Okay, what we're going to do is we're going to talk about Chapter 8 today. What this is for is I'm going to be gone this week, so we're going to do the lecture on a video, and I'm going to have you watch some other videos from Big Bad Tech about direction control valves and how they operate and so forth. So we're going to describe the purpose, construction, and operation of various flow control valves. We're going to analyze how flow control valves can control the speed of hydraulic cylinders. We're going to differentiate between non-compensating and compensating flow control valve. We're going to describe the purpose, construction, and operation of mechanical, hydraulic, and electrohydraulic servo valves. And we're going to discuss the purpose, construction, and operation of cartridge valves. One of the most important considerations in a fluid-powered system is the control. If components are not properly selected, the entire system will not function as required. Fluid power is controlled primarily through the use of control devices called valves. The selection of these valves involves not only the type, but the size, actuating type, and remote control capability. One of the most important considerations in a fluid-powered system is control. If control components are not properly selected, the entire system will not function as required. Fluid power is controlled primarily through the use of control devices called valves. The selection of these valves involves not only the type, but the size, actuating type, and remote control capability. Directional control valves determine the path through which fluid traverses a given circuit. The control of the fluid path is accomplished primarily by the valves, shuttle valves, and 2-, 3-way, and 4-way directional valves. Pressure control valves protect the system against overpressure, which may occur due to the excessive actuator load due to a closing of a valve. Fluid flow rate must be controlled in various lines of the hydraulic circuit. You have non-compensated flow control valves are used where precise speed control is not required, since flow rate varies with pressure drop. Adjust to changes in pressure drop to produce a constant flow rate. Pressure-compensated flow control valves automatically adjust to change pressure drop to produce a constant flow rate. Directional control valves are used to control direction of flow in hydraulic circuit. The number of ports on a directional control valve, it's called DCV, is identified using the term way. Thus, for example, a valve with 4 ports is a 4-way valve. And here's one here. Okay, it's got four ports right here. Okay, and so this is a 3-position valve with transverse condition. It's a 3-position valve. So each envelope is a position. Okay, it's a 3-position 4-way valve. The simplest type of directional control valve is a check valve. You can look on page 263, which is a 2-way valve because it contains 2 ports. The purpose of the check valve is to permit free flow in one direction and prevent any flow in the opposite direction. If you took electronics, it's like a diode in an electrical circuit. It only allows fluid to flow in one direction. And here's what it looks like. Okay, you can see the symbol there. Any pressure coming from the left is going to seat that little ball on its socket, but the flow coming from the right will knock the ball off the socket and the fluid will flow, just like it shows right here in the illustration. And here's another one, inline poppet valve type check valve. Okay, so it shows you how that works. And then is what the check valve looks like inside, and then there's the symbol here. Okay. Now this is a typical right angle check valve. Okay, essentially you've got fluid coming in through the bottom. Okay, and it will go out. Okay, but it's not going to go the other direction. It's like coming in here. It's not going to go anywhere. The fluid's going to pop this off. It's based on the tension on the spring. and they're adjustable on some of them. Here we have a right angle check valve with the orifice. Okay, now the orifices, you have a needle seat. If you're familiar with carburetors, they used to have a needle and seat, and as the float ball came up and down, it would adjust the amount of fuel coming into the float bowl. This does the same thing. Okay, a pilot-operated check valve is a valve that permits free flow in one direction but permits flow in the normally blocked opposition direction only if the pilot pressure is applied at the pilot pressure port of the valve. Pilot check valves are frequently used for locking hydraulic cylinders in position. And here's one here now. Here's where your pilot fluid comes in. And this is the symbol here. Okay, they have these symbols, this pilot line drawn a lot of different places on these symbols, but if it has it there as a pilot line, you'll see it. And there you go again with a different type of pilot. Okay, it's not, the fluid's coming in, but it's not doing anything because it's locked. But if the pilot comes in and opens it, and we go back to the other one, let me show you something. Okay, here you get pilot voltage fluid coming in. Right now your regular flow is blocked. Once the pilot opens this up off the seat, it moves this up and lets the fluid come through this way. And it's all through the pilot fluid. Okay. And then here's another one, a pilot to close check valve. It uses a pilot to close it instead of opening it. And here's some circuits with how they work. Okay. And now the three-way valve, the three-way directional control valve, which contains 3 ports, are typically of the spool design rather than poppet design. A spool is a large circular shaft containing lanes that are large in diameter. Sections machined to slide in a very close-fitting bore of the valve body. The grooves between the lanes provide the flow path between the ports. These valves are designed to operate with 2 or 3 unique positions of the spool. Spool can be positioned manually, mechanically, by using pilot pressure, or by using electrical solenoids. Here's one here. Okay, this is a 3-way 2-position. Okay, and you can see here's your tank, and there's your pressure. Then there's your output A, and it's going to show you whether, okay, right now this direction it's working this way. So essentially it would be in this position here. And in order to get the fluid to go up, it has to shift over here to the left. Now 4-way valves. Now figure 8.8 shows the flow path through a 4-way 2-position directional control valve. Observe that fluid entering the valve at the bottom port can be directed to either port A or B. Following is a description of the flow path through the 4-way valve. Here you have the 4-way valve. Okay, it's got 4 ports, 2 positions, and in right here the pump is going to port A, which is this right here, and I mean B, and A is blocked. See where A doesn't have any flow to anywhere, back to the tank or anywhere. Now in this position here, you have pressure going in this way, so it would be this right here. Is the drawing would relate to that physical, the way it looks in the direction control valve. And again, here's one with a crossover and straight through. Okay, the tank goes to A, and the pump goes to B. So depending on how they're hooked up to the actuators, you're either moving the actuator in or out. Okay, and in the other direction is going, the pump is going to port A and the tank is going to port B. Okay, a very common way to actuate a spool valve is by using a solenoid. When the electric coil's solenoid is energized, it creates a magnetic force that pulls the armature into the coil. This causes the armature to make the push pin to move the spool valve. So there's a push pin that pushes it. We'll look at some of those here. Most three-position valves have a variety of possible flow path configurations. Each four-way valve has an identical flow path configuration in the actuated position, but a different spring-centered flow path. Note that the open-centered type connects all ports together. In this design, the pump flow can return directly back to the tank at essentially atmospheric pressure. At the same time, the actuator, cylinder, or motor can be moved freely by applying an external force. And here's some of your ways that they do this. Okay, this is where it's going back to the tank. Okay, and it's going back here. There's this position here. You're looking at your pressure and your tank, and you can see how they're working there. And this is out of your book, so you should be able to find it in the book. And this is another way to look at it. Now, one thing about this right here, look, this symbol means it's solenoid operated or manually, but here is spring centered. Okay, so basically it always springs back. What's happening is when the solenoid energizes, it pushes this spool to the left and changes the direction from straight through to crisscrossed. Okay, and once the solenoid is de-energized, then the spring centers back to where you have straight through. Okay. And here's another one. This was shown with two solenoids to move either left or right, and it also has two springs. So if neither one of these solenoids are energized, the springs will center to where this one is here. All ports are blocked off. It's a four-way, three-position direction control valve. Here's a four-way, two-position valve with one solenoid on it. The spring returns it back to the right. The solenoid pushes it to the left. And this is how it works. It's kind of got a little coil around it, energizes the coil and moves that armature and moves this, because it just moves the shaft left to right or to the left, and then the spring moves it back to the right once the solenoid's de-energized. Now here's a manual connection, and it's latched. See, it's got a little pawl on it, so whatever position you put it in. See, there's no springs, so you can move it back or forth any position you want. So this is a four-way, three-position valve. Okay, so here you have, and this is the way they're usually on a plate where the cables come up through where this is mounted to, come through the bottom. And then here's some others. This is the same valve where all of them, it's center. Okay, and then it's moved in one direction, and it's going to just circulate the fluid. This circulates it and blocks the A and B port, and this one here lets it drain back to both ports, drain back to the tank. I think, yeah, it's a T. Again, the T stands for tank, and P is for pressure. A and B is for your cap and rod end of your actuator. Again, this is a manually operated, spring-centered, three-position, four-way control valve. And you can see there's no latch and little pin pawl. So this, once you put it somewhere and release it, it's going to spring center because you got springs on both sides. This is something where the direction control valve is controlled by moving parts on a line or in a machine. That's usually like a cam follower system. And then this is a solenoid on both ends. This is what it looks like. Basically, it's a four-way, three-position valve, spring loaded and solenoid actuated on both ends. Okay. Once both solenoids are de-energized, the springs will center it, put it back to the center. If this solenoid energizes and moves it to the right, okay, and then another operation comes along, it de-energizes this and then energizes the solenoid here. That's usually done. PLCs are usually programmed to do this type of control this type of device. And again, this is a pilot type. Okay, it's hydraulic fluid because the little arrow is painted dark. And these pilots, if there's pressure on these pilots, it will activate this and move the. If there's fluid on this left side connection, it will move the spool to the right and make it where you're crisscrossed. And if you got fluid on the right, on the left, on the right side, it's going to move it to the left, and then you'll have straight through. And then when there's no fluid, it's spring centered, so it's going to go back to the center where all ports are blocked. And here is another type of actuator, direction control valve. That's it's a push type. You can use it manually to activate it or electronically. This shows a little bit of the magnetism, what it takes to energize that solenoid. And there's it activated, and then there's it moving back. You see it, you got changing direction, and it's going to make it activated. Okay, and this is a another type. It's a air gap solenoid, and then here's a wet armature type. Now this is how you'll see some of the direction control valves set up in the system. This is your motor that's driving your pump. Okay, this is your line going from the pump to the tank, and this is the outlet going to the pilot. It's got a little bit of voltage fluid here, and then here you have a check valve. Okay, and it's keeping fluid from coming back into the pump, but you also have this relief valve system. So if you have so much pressure buildup with this thing right now, is just at this position is putting fluid back into the tank. Okay, you can have these are all going to the same location. You draw them in these circuit diagrams to make it easy. It's like the ground in an electrical circuit. And then these ports are blocked on A and B. So once you get some pilot fluid here, it's going to move it to the right and crisscross this, and whatever this A and B are connected to is either going to move that actuator in or out or turn that motor in one direction or the other if it's a hydraulic motor. And then this is another way of doing it here too. Again, these are some more drawings in the two-stage valve system, okay, where you can have two stages of direction control valves. One stage is controlling the second stage. And then this is a high flow position relief valve, and it should show you how it operates there. Okay, so what you have is you have your pilot to open and you have a pilot to close, and then there's a sensor there. So essentially you use the pilot fluid to actuate this plunger to close it or open this device. And once it's activated, it's closed it and there's no more fluid flow. Okay, it's pushed back down. Go look at that again. Okay, so you have fluid flow everywhere, and then boom, stops. Okay, now this is a shuttle valve. This is a symbol for it. And pressure control valves, they're central pressure relief valves. They're most widely used pressure control valve is a pressure relief valve, since it is found in practically every hydraulic circuit. That's that valve system that I pointed out by the pump. It is normally a closed valve whose function is to limit the pressure to a specific maximum valve by diverting pump flow back to the tank. The poppet is held seated inside the valve by a force of a stiff compression spring. When the pressure reaches a high enough value, the resultant hydraulic force acting on the piston-shaped poppet exceeds the spring force, and the poppet is forced off of its seat. This permits flow through the outlet to the tank as long as the high pressure level is maintained. And once that high pressure level is down, and it's going to shut that valve off. Note that the external adjusting screw, which varies with the spring force and thus the pressure at which the valve begins to open. That's called your cracking pressure. Okay, so here's a little drawing. This is in your book also. It's 831 and drawing at 831. And there's a formula that we're going to go over that's going to talk about this cracking pressure. I wouldn't be too concerned about it. What I want you to do is be familiar with it so you understand what that is and how it works. And then there's the method of figuring it out. Okay, I'm not going to go over it, but essentially that's in your book there too. Let me see, hold on. Yeah, here, it's on page 277. And there's the rest of it. And then this is how the circuit looks. Okay, you have your filter, your tank on the left there. There's your pump. And then up top is you go to your hydraulic system, to your direction control valve. And this is your pressure relief valve. If there's too much pressure up here, it builds up in this system. So this pump is producing the flow, but it's getting a lot of resistance to flow. Guess what it creates? It creates pressure. Is resistance to flow. And once that resistance gets up to like 500 psi, then it starts diverting the flow from the pump back to the tank instead of up here. That's how a pressure relief valve works. Now, a compound pressure relief valve is one operates in two stages. The pilot stage is located in the upper valve body, and the pilot stage, and that contains a pressure-limited poppet that is held against the seat by an adjustable spring. The lower body contains the port connection. Diversion of the full pump flow is accommodated by the balanced piston in the lower body, and that is shown on page 278. And here's some pictures of them. Okay, and the view A is the unit is closed, and you can see there's your inlet. Okay, and you're not getting any flow. The spring holds the piston closed down, and it's down this way. Okay, and then when the valve setting is reached, the poppet opens, limiting the chamber, limiting pressure in the upper chamber. Okay, so then this is how you adjust it. And then the piston moves up to divert pump output directly back to the tank. Okay, and so that's how that does that. Manual override of the solenoid return spring is a standard feature. Pressure relief valve is vented when the solenoid is de-energized and devented when energized. Pressure reducing valves. A second type of pressure control valve is a pressure reducing valve. This type of valve, which is normally open, is used to maintain reduced pressure in specific locations of the hydraulic system. It is actuated by downstream pressure and tends to close as the pressure reaches the valve setting. The figure below illustrates the operation of a pressure reducing valve that uses a spring-loaded spool to control the downstream pressure. And again, it's got your It's an adjustable spring, and you turn this knob to get it, and this is your symbol for it. Most of them are this kind on the pressure relief valves. Now, unloading valves, this is used, it's an additional pressure control device, and this valve is used to permit the pump to build pressure to an adjustable pressure setting and then allow it to discharge oil to the tank at essentially zero pressure as long as the pilot pressure is maintained on the valve from a remote source. Hence, the pump is essentially no load and therefore developing a minimum amount of power. So if you want to lock an arm in place or something like that, another valve you could do that with is a sequence valve. This is not the same with a pressure relief valve because the pump is delivering full pump flow at the pressure relief valve setting and thus it operating at maximum power conditions. Unload valves. The figure below shows a schematic of an unload valve used to unload the pump connected to port A when pressure at port X is maintained at the valve that satisfies the value setting. The high flow poppet is controlled by the spring-loaded ball and the pressure applied to port X. Okay, so here's port X. It's coming in here, and this is a schematic of it, of how it works. Okay, and this is how you adjust it. And see this top side pressure on the main poppet to go to a very low value and allows flow from A to B with a very low pressure drop as long as the signal pressure at X is maintained. And then the ball reseats and the main poppet closes with a snap action when the pressure at X falls to approximately 90% of the maximum pressure setting of the spring-loaded ball. And so it's kind of how that works. It's kind of a neat little device, you know. Sequence valve is control valve is just designed to cause a hydraulic system to operate in a pressure sequence. After the components connect to the port A have reached adjusted pressure of the sequence valve, the valve passes the fluid through port B to do additional work in a different portion of the system. The high flow poppet of the sequence valve is controlled by a snap-loaded cone. Flow entering at port A is locked by the poppet at the low pressure. The pressure signal at A passes through the orifice to the top side of the poppet and to the cone. There is no flow through these sections until the pressure rises at A to the maximum permitted by the adjustable spring-loaded cone. There is no flow through these sections until the pressure rises at A to the maximum permitted by adjustability set spring-loaded cone. When the pressure at A reaches that value, the main poppet lifts, passing flow to port B. It maintains the adjustable pressure at port A until the pressure at B rises to the same value. A small pilot flow, about a quarter gallon per minute, goes through the control piston and past the pilot cone to the external drain at this time. When the pressure at B rises to the pressure at A, the control piston seals and prevents further pilot flow loss. This main poppet opened fully and allows the pressure at A and B to rise to higher values together. Flow may go either way at this time. The spring cavity of the control cone drains externally from port Y, generally back to the tank. This sequence valve may be remotely controlled from vent port X. And there it is. Okay. Essentially, it's similar to, you can see the drawing there to what the symbol looks like for it. See, it's kind of pilot fed. That's what that little dotted line is. Now, counterbalance valve purpose in life is to maintain control of a vertical hydraulic cylinder to prevent it from descending due to the weight of its external load. As shown in the figure, below the primary port of this valve is connected to the bottom of the cylinder, and the secondary port is connected to a directional control valve. The pressure setting of the counterbalance valve is somewhat higher than it is necessary to prevent the cylinder load from falling due to its weight. Okay, here we have it. There's your symbol. Okay, and um, essentially that's your your directional valve, control valve. Just is blocked out with that, and there's the flow to the spool. This is your actuator or your load. Okay, and you're trying to keep this piston from falling down. So the counterbalance valve keeps it in the static pressure, so you don't have the pump holding it, putting pressure on it all the time. Flow control valves at Orifice has a flow meter or flow control device. Figure below on page 285 shows an orifice. It's a disc with a hole through which the fluid flows, installed in a pipe. Such a device can be used as a flow meter by measuring the pump pressure drop across the orifice. This is because for a given orifice there is a unique relationship between pressure drop and the flow rate through the orifice, and thus the flow rate in the pipe. Again, you remember that the pump produces flow. Any restriction in that flow is where your pressure is generated. So by putting those orifices in there, you have this little here formula here. You can figure out the flow rate, and that's a constant that they put in there. C is a coefficient of in the area of the orifice opening, so you know the diameter. Then you can figure out the area, which is area equals pi divided by 4 times diameter squared. And so you do that. And you also need to know the specific gravity of the fluid, which you can get off the spec sheet for it. And this is what it looks like. This is what they show in the book. Now, needle valves or flow control valves are used to regulate the speed of hydraulic cylinders and motors by controlling the flow rate to these actuators. It may be as simple as a fixed orifice or an adjustable needle valve. Needle valves are designed to give fine control flow in small diameter piping. As illustrated below, the name is derived from the sharp pointed conical disc and matching seat. Again, that's similar to what you had in carburetors. You guys remember what those are. If you look, I think this next drawing here has it. See that right down in here is a little round tapered hole that this pointed object flows in. And you turn that knob and it pushes it back down into that hole and it stops the flow. So you can get precise flow. And then these are for a given opening position, a needle valve behaves as an orifice. However, unlike an orifice, the flow area is in the needle valve can be varied and it's tapered, so you don't know what the full area is. Thus, the equation below can be modified as it follows to represent the pressure drop versus flow rate for a needle valve. You're not really worried about calculating the flow rate. You can see the changes in pressure, which are what you're looking for. You're making it more restrictive, so the pressure would go up. Non-pressure compensation. There are two basic types of flow control valves. You have the non-pressure compensated and pressure compensated. The non-pressure compensated type is used where the system pressure are relatively constant and monitoring speeds are not too critical. They work on the principle that the flow through an orifice will be constant if the pressure drop remains constant. The figure below illustrates a cutaway view of a non-pressure compensated flow control valve and its graphic symbol. Here, there you have that's what it looks like, and it's cut away so you can see how that changes the flow there, the little non-pressurized compensating flow control valve, okay? And then if a load on an actuator changes significantly, system pressure will change appreciably. Thus, the flow rate through a non-pressure compensated valve will change for some flow rate setting. Figure below illustrates the operation of a pressure compensated valve. And again, you see where it has the to overcome the pressure of that spring. The servo is a directional control valve that has infinitely variable position capability. Thus, it can control not only the direction of fluid, but also the amount. Servo valves are coupled with feedback sensing devices, which allow for the very accurate control of position, velocity, and acceleration of an actuator. The figure below shows a mechanical type servo valve, which is essentially a force amplifier used for positioning control. In this design, a small input force shifts the spool of the servo valve to the right by a specific amount. It all then flows into port P1 and retracing the hydraulic cylinder to the right. The action of the feedback link shifts the sliding sleeve to the right until it blocks off the flow to the hydraulic. See how it moves that piston back and forth. Hydraulic cylinder. Thus, a given input motion produces a specific and controlled amount of output motion. Such a system where the output is feedback to modify the input is called a closed-loop system. One of the most important applications of this type of mechanical hydraulic servo valve is hydraulic power steering systems of automobiles and other transportation vehicles. Electrostatic servo valves. These typically are used in an electrical torque motor, a double nozzle pilot stage, and sliding spool second stage. The figure below gives a cutaway view of an electrohydraulic servo valve. Servo is electrically controlled proportional metering values suitable for a variety of mobile vehicles and industrial control applications such as earth-moving vehicles, articulating arm devices, cargo handling cranes, lift trucks, logging equipment, farm machinery, steel mill, convert. There's a fair amount of things that this can work in. Okay, and they look at page 294 and you can see that same drawing and how it works. It has the magnet, the armature, the coil, the nozzle, and it has a spool that it moves. And then you have your connections down below. The four-way valve spool directs the flow from the supply pressure port to either of the two outlet to load ports in amount proportional to the spool displacement. So it's based on how much that spool is going to move. And the spool contains flow metering slots in the control lands that are uncovered by the spool motion. Spool movement deflects a feedback wire that applies the torque to the armature flapper. And that's that little device in the middle. Electrical current in the torque motor coils cause either clockwise or counterclockwise torque on the armature. This torque displaces the flapper between the two nozzles. Different nozzle flow moves the spool to either the right or the left. The spool continues to move until the feedback torque counteracts the electromagnetic torque. Now, electrohydraulic servo valves. At this point, the armature flapper is returning to the center, so the spool stops and remains displaced until the electrical input changes to a new level. Therefore, valve spool position is proportional to the electrical signal. That's where you can have a PLC that's actually outputting different voltage levels based on what it's getting for a feedback to allow positioning that device that's being controlled by this valve in a precise manner. Proportional control valves, which are also called electrohydraulic proportional valves, are similar to electrohydraulic servo valves in that they both are electrically controlled. However, there are a number of differences between these two valves. In servo valves, electrical current in a torque motor coil causes either clockwise or counterclockwise torque on an armature to control the movement of the valve spool. On the other hand, a proportional valve uses a solenoid that produces a force proportional to the current in its coils. Thus, controlling the current in the solenoid coil, the position of the spring-loaded spool can also be controlled. This means that unlike a standard solenoid valve, a proportional valve can provide both directional and flow control capability in a single valve. And here's what it looks like. Okay, and that's its symbol for it. And you can see that it's a pretty snazzy device. It's a 4-way 3-position valve, and it's pretty well self-contained. You can see it's spring-loaded, and it's got these solenoids on it. Market pressure and worldwide competition make the need for more efficient and economic hydraulic systems greater than ever. When you see that in robotics and a lot of other precise type of equipment, milling machines that are doing a lot of movement with those. Integrated hydraulic circuits offer a proven way to achieve these improvements. Integrated hydraulic circuits are compact hydraulic systems formed by integrating various cartridge valves and other components into a single machine-ported manifold block. The use of cartridge valves in a ported manifold block provides a number of advantages over discrete conventional ported valves mounted at various locations in pipeline of a hydraulic system. And advantages include reduced number of fittings to connect hydraulic lines between various components in the system. It also reduces your oil leaks and contamination due to fewer fittings, lower system installation time and costs. It reduces service time since faulty cartridge valves can easily change without disconnecting fittings, and smaller space requirements of the overall system makes it more efficient. And a variety of different valve functions can be provided using cartridge valves. These include directional control, pressure relief, pressure reduction, unloading, counterbalancing, and sequencing, and flow control capability. Integrated hydraulic technology can provide easier installation and serving greater reliability, reducing leakage, expanding design flexibility, and lighter, neater hydraulic packages for a variety of hydraulic applications. Now, hydraulic fuses are analogous to the electric fuse. It prevents pressure from exceeding allowable value in order to protect circuit components from damage. When hydraulic pressure exceeds a design value, the thin metal disc ruptures to relieve the pressure as the oil is drained back to the tank. After rupture, a new metal disc must be inserted before operation can be started again. So it's like a fuse because it blows when the pressure gets too high. Below is a schematic of the hydraulic fuse and a schematic symbol. And see here, there's your little thin disc, okay? And once it gets up too high, it pops this and it drains the fluid back to the tank. And that's what this symbol is here. And that's it. Now, what I have some videos on directional control valves that I've put up on Blackboard that I need you to watch also. And then there'll be a quiz for this chapter 8 that's on Blackboard that you will need to take and turn in before Sunday, which I think is October 1st or 2nd or something like that. And but it's written in the instructions on taking the quiz. And what I use that for is I use that to show that you actually learned something on this chapter. You watch the videos and put some time into it. So if I see that you have the test done and you got a good grade on it, then you get good attendance. So anyway, good luck on this. And if you have any questions, you can email me at jmurphy@trcc.edu.